All right, we are going to talk about introduction to structural member properties, commonly known as beam deflection. In front of you for this activity, or for this video, you really just need your notebook and pen, and I'll tell you what notes you need to write as we move along. All right, first thing you'll need to jot down is moment of inertia. And moment of inertia, basically right here in blue, it's the stiffness of an object related to its shape. If you look at the diving board on the left, it's supposed to be springy, and that has to do with its shape. But if you look at the starting blocks on the right, they are not supposed to be springy, they're not supposed to give. It's supposed to be a rigid surface in which the swimmers start a race off of. So stiffness of an object related to its shape. Where this is commonly seen, and the example that we're going to use in class has to do with joists in a house. If you're in your basement, maybe an unfinished basement where you can see the floor joist above you, then you've probably seen a joist on its edge like this, versus like hardwood floors in a house are facing this way, and that has to do with its strength. So what distinguishes A from B? Well, you can probably already realize that you're going to have way more deflection with this beam versus this one. It's a lot stiffer in this orientation. Again, stiffness related to its shape, either vertical orientation or horizontal orientation. All right, we can calculate moment of inertia, and let's jot down this equation. I sub xx, and this just has to do with along the x-axis. That's not really important. And bh cubed over 12. Let's jot that down, and let's draw this rectangular shape. So those beams I just showed you, imagine if you're looking at one, like a cross section of that beam. Something to make note of in your notes. Might be a good idea to put parentheses around the h cubed, or you'll get in trouble when you're doing your math. It's just the h that is cubed, not the b. So bh cubed over 12, and 12 is a constant. Let's do an example. You can go ahead and jot this one down, and let's show your work for these 3 steps. This beam is 1.5 inches on its base, 5.5 inches tall, cubed over 12, and then we simplify, and then we'll finally get down to our final answer, 21 inches to the 4th. And notice with inches, there are no units on 12, nothing canceled, and that's why we get inches to the 4th. Inches to the cubed times inches, that's how we get inches to the 4th. Please make sure you're following along with your calculator. You'll be doing this on a quiz at some point. So if we turn the joist on the side, you don't have to write this part down. If we turn it on the side, you'll notice we get a much lower moment of inertia. It is much less stiff. It's actually 14 times. This one in a vertical orientation is 14 times stiffer. That's why we used joists, floor joists, and roof rafters on their edge in homes. You know, think about the amount of snow that a roof rafter has to hold up in the winter, plus the weight of the roof itself. Okay, with building materials, a lot of times we'll see these what are called composite shapes. So think about using a solid piece of steel versus maybe this L shape, this box shape, this C shape, or what's really commonly used as an I-beam. Why might we use that versus a solid piece of steel? A solid piece of steel has to be stronger, and it is, but it really comes down to 2 things. One, it costs way less to make some composite shape like this I-beam, and if you look at the math, a huge reduction in area, which of course is going to cost less. And yes, the moment of inertia isn't as stiff, but you still get a very stiff member or a very stiff beam with using way less material. Yeah, doing more with less. All right, next thing, modulus of elasticity. That's often abbreviated with a big capital E. And what that basically means, down here in blue, defines the stiffness of an object related to its chemical properties. That's a great definition. Stiffness related to chemical properties. And then it goes without saying, the higher the modulus of elasticity, the greater resistance to deformation. Deformation just means bending. So if I have a higher modulus, well, then it's not going to bend as much. Let's see. So speaking of, we have two different beams here. A might just be a traditional piece of wood, and B might be like a Trex material, something made out of plastic. And they're both, notice they're in the same orientation, so they have the same moment of inertia. But what distinguishes them is their modulus of elasticity. And let's move on to, oh, I think I passed it. Let me back up a little bit. Yeah, it says what distinguishes A from B. Will beam A or B have the greater resistance to bending, resulting in the least amount of deformation if an identical load is placed in the same location? So yeah, the composite one in this case is going to deflect way more than the traditional wood one. So not only does it have to do with its orientation, its moment of inertia, but it has to do with its modulus of elasticity, what it is made of. Okay, last thing is beam deflection, or sometimes called delta max. And let's see, hold on, don't write anything. And we're just going to move right into our equation. And yeah, you can go ahead and copy this one down. I think it will appear on the next slide too. Yeah, here we go. Okay, so delta max, so the max amount that this beam is going to change or deflect when a load is applied, in our case, in the middle. So that's what delta max means, the max amount of change. We will have some force. Go ahead and write your equation and then start substituting and solving. Some force, in this case 250 pounds of force. This is, again, has to be right in the middle to use this equation. Length is in inches. Please make a note off to the side. Length has to be in inches. Commonly these beams are given as an 8-foot beam. It's not given in inches, so length has to be in inches. Also, while we're here, it would not be a bad idea, again like we did before, FL cubed. It's not FL and then cubed that product, just L cubed. So our weight, 250, in this case 96 inches cubed, and 48 E, that's our modulus of elasticity, and that would just be, that would be given. That has to be given in a chart. In that case, in our case, it's down here. And then this is our moment of inertia that we found earlier, way back in the beginning of the video. Please make sure you're working through this on your calculator. Make sure you're getting this answer. Most of the time, if you, so ignore these parentheses. If you just put the numerator in parentheses and put the denominator in parentheses, you should be fine. But please make sure you're getting this answer. So this is just showing two different beams. That last one was 0.12. Yep, the wood beam. And then remember, this was the plastic. It's going to deflect a lot more. That's why it's deflecting a ½ inch. And you might think like, oh, a ½ inch, that's not a big deal. Think about the ceiling of your house. What's it made of? It's made of plasterboard, and it does not take a whole lot of force to actually crack that plaster. Think about that happening on a multi-story building throughout the entire building because someone did do some math right, and we have cracked ceilings all over the place. That could be a huge problem. All right, after this video, make sure you check off your notes with me, and then looks like you'll move on to your activity.